Hello and welcome everyone to Ethproofs call number 10. This is a really special call on what might become the future of hash-based proof systems. We're going to be focusing on binary fields, which is a big move away from the prime fields that are in production today. If you're new to the Ethproofs call community, we have a corresponding Telegram group. So that's Ethproofs_community. And we also have a QR code here if you'd like to join. Alex, would you mind muting yourself? We've had 12 Ethproofs calls so far, a few B calls. Yeah, we started in 2025. And the next Ethproofs call may be on Fiat Shamir. There's been a little bit of a development, and the tentative date that we have here is October 2nd. So Fiat Shamir is like one of the last few subtle things that we want to try and get right to have really amazing security. So on Fiat Shamir, last year we had this paper, How to Prove False Statements by Dmitry, Ron, and Lev. And we're going to have a bit of alpha. We're going to have a new paper by Giacomo with another set of edge cases to be careful of. And I think this is a good prompt to basically have a bigger discussion on Fiat Shamir. Okay, now on the topic of today's call, binary fields. So yesterday, we made a big announcement on Twitter, basically that the EF is moving away from Poseidon and is going to be embracing traditional hash functions. And the way we can achieve that without losing performance is really to have these new breakthrough snark proof systems that are hash friendly or friendly to binary circuits and Boolean operations. And here are some of the top questions that I've received since yesterday, and I guess I want to quickly go through them one by one. So the first question is Poseidon broken? So to my knowledge, as of today, Poseidon is not broken. It still has 128 bits of security. There are multiple teams that have partial attacks that all nibble at the security margins, and we will have in October a Poseidon cryptanalysis workshop with 15 world experts. They're going to be spending 3 days in a room, and the one goal of this whole cryptanalysis workshop is going to be to break Poseidon. And if it survives this workshop, I think there's going to be a tremendous signal for Poseidon in terms of its security. If it breaks during the workshop, I think that's also going to be a positive outcome, because it might be a forcing function to start retiring and migrating away from Poseidon and having more unity and less fragmentation within the space. Another question is, what about multi-party computation and threshold signatures? So once we have the snark functionality that we use for aggregation, we can reuse it for threshold signatures. So imagine having a k out of n scheme. We just do it the most naive way possible, where we have n parties, each with n independent pub keys, k independent signatures that get produced when a message gets signed, and these k signatures just get folded into the one proof that we have per block. So in some sense, the approach that we're taking gives us threshold signatures and MPC for free, and we can even do like super fancy multi-sig, so it could be 2 out of 3 or like 5 out of 7 or whatever programmable conditions you want to have. Another question is, what about the complexity of snarks? Well, here the answer is easy. This has been the answer that we've given for many years now. It's end-to-end formal verification. Another question was, what about the performance on hardware wallets? Hardware wallets can only process about 10,000 hashes per second. Well, we still have work to do here, but we believe we can design a stateless signature scheme, basically something that we're calling lean sphinx, and it would have a hardware wallet signing time of roughly 1 second. And then another question that we got is, okay, you're moving away from Poseidon, but which hash function are you embracing? And the honest answer here is we don't know. If you haven't muted yourself, please make sure to do so. But yeah, if you're familiar with the Ethproofs calls, we've already done one change away from Poseidon 2 to Poseidon 1. And if you had asked me 2 weeks ago, the top candidate would have been Blake 3. But now, every time that we improve the performance, we're kind of opening up the design space of possible candidates that would have the performance that we want. So now, we're starting to explore Blake 2S, and the performance has gotten so incredibly good in the last few days that, even SHA-2, which is the slowest of all, by roughly 2x relative to Blake 3, at least within a snark is looking, potentially very good. But again, we haven't made any decision as of yet. So this whole area of binary field proof systems really kicked off with the Binius paper in 2023 by Ben and Jim. And in recent weeks, we've had this Flock paper by Benedict, Ron, and William that really took it to the next level in terms of making it much more applied with performance, which is really competitive with state-of-the-art systems. And nowadays, we have this really incredible new tool called Open Auto Research Challenges. So one of them is snark.fast, and it took the performance of Flock and improved it by 3.5 times on a MacBook laptop, getting us to 1.8 million compressions per second for Blake 3, which is absolutely amazing, given that this computer is it's an M3, so it's 2.5 years old now. Now there's another very interesting auto research challenge called zk.golf. They have also embraced binary fields, so their challenges 7 and 8 are regarding arithmetizations of SHA-2 and Blake 3 with binary fields, and they've both squeezed about 30% relative to Flock. So the 1.8 million number here is actually a bit misleading. It should be closer to 2.3 million once we have these optimizations incorporated. And there's even more optimizations that are in the pipeline that are going to be announced later today that might get us closer to 3 million hashes per second. So here's the agenda. We have a very quick update from Jordi, and then we have a section on auto research. So we're going to be discussing zk.golf, snark.fast, and there's a really exciting unveil and new challenge that is dropping today. So Alex Hicks will be making a presentation on this very exciting new auto research challenge. And then we have 9 presentations on binary fields, going through Flock, Binius, but all sorts of other new and some unpublished ideas here that are going to take binary fields to the next level. So without further ado, I would like to invite Jordi to the stage to give us a quick update on ZISC.
Can you hear me?
Yep.
Can you see the screen? Okay.
Yeah.
Well, just glad to announce that in this we are continue working and we are ready to launch this 1.1. We are going to launch it either today or maybe Monday morning. And the main advantage. The main thing is about optimizations. I mean, in the last month, we have been working a lot of optimizations, and this is the current state. So with 4 5090s, keeping all the security parameters, 128 bits probable security. We are still using Poseidon 1, but not Poseidon 2. So we already step back to Poseidon 1. And of course, keeping everything of post-quantum. These are the numbers. I mean, we are the 99% percentile is below 10 seconds, and the average, it's less than 6 seconds. And this is just with 4 5090s. This is a little bit the distribution that you can see. This is our, it's like recent more than 7,000 blocks, and this is the distribution that we are getting. What we did, it's a lot of engineering here. Here I just highlighted some of the things that we did. First is we are using a new client, is CSCAF1. Mainly it's based on EVM1, it's a C++ with some optimizations that are there. There is a lot of the MOPS is memory operations. We are running in things that are moved from the CPU to the GPU. A lot of GPU re-engineering. We converted some interpret of the what we call expressions to something that's compiled directly to the expressions in the GPU. We did a lot of improvements in the limitations, especially here is Blade 2 and other that we save a lot of things. Here we also implemented the RISC-V, all the bit manipulations. This give us smaller proofs with less compilations, and we also added a new precompile. This is for the analysis of the jump test. This also gave us a lot of burst here. Plus we also did a faster BLS 381 and the BN254 precompile. So this is very much a lot of the engineering that we've been working in the last works. I'm very excited for what's going on these binary fields and see how we can even improve better further with that.
Amazing. Congratulations, Jordi. I would never have expected real-time proving with 4 GPUs. This just means that we can increase the gas limit by 4x. And one of the amazing outcomes from the last few weeks is that it seems like binary fields are actually faster, significantly faster potentially for the glue logic than prime fields. So yeah, very, very bullish times. Any questions for Jordi? If not, we're going to move to Matthias, who will discuss zk.golf. Jordi, do you want to stop showing your screen?
I'm trying. It's just...
Oh. There we go. Yes, perfect.
Does that work?
Yes, nice.
Perfect. Yeah. So I guess zk golf kind of came out of sort of a realization or a potential that developers essentially shouldn't be writing circuits anymore. They should be writing sort of high-level specifications and then asking an LLM to come up with like an implementation and repeatedly optimize it. And we figured like the best possible demo we could do of this is what's zk golf. So what's zk golf? So essentially in zk golf, we write some sort of a specification of a circuit. Essentially, what should the circuit do? So it's just like a program that computes whatever you want the circuit to do. So it's like sort of a traditional implementation of, say, Ketchup. And then everybody and their agents can compete to write the most optimized version of the circuit. And we can sort of trust these agents to do that because they also need a proven mean that the circuit is complete. In other words, if the original program actually outputs something on some particular input or is satisfiable, then so is the circuit. And conversely, it's also sound. So if the circuit is satisfiable, then it also satisfies the original program, the specification. So for large fields, which is what we ran it for the longest, so we ran it on large fields with R1CS, so motivated by Graph16. It's resulted in some extremely optimized circuits. So what's new? Of course, the new thing is that now we also have subcircuits over binary fields. And specifically, we are targeting what we call canonical R1CS, which is a version of R1CS where everything is square and where the C matrix is an identity. So it's like A times Z, Hadamard product B times Z is, Z itself. Equivalently, it means that like every row is like some sort of that every variable in Z is like written as some set of some sum of Zi elements times some other sum of Zi elements. And there's exactly one constraint on each one of the entries. And this was motivated by Flock, where it's also restricted to this limited version of R1CS. So in the first batch of challenges that we released, we have added SHA-256 compression and Blake 3 compression, as well as Kangaroo 12 permutation, which is a round reduced version of Keccak permutation. We've seen, like here, the numbers compared to what Justin was showing. Here the numbers is in relation to the previous best circuit. So we have a 27% reduction and a 29% reduction compared to the previous best known circuits at the moment. Although for Keccak or Kangaroo 12, we still just have the matching thing. It's because if you know how Kangaroo 12 or like Keccak works internally, it's very straightforward. So it's not so clear that there's great ways to optimize it. But the other ones have, for instance, modular arithmetic. So with that overview done, we're open for suggestions for the next binary circuit or other circuit that you would like to see on CK Golf. The hope is to release a circuit library of formally verified, extremely optimized circuits for basically any type of primitive that you would want. So we would like to hear your suggestions. And I guess one other observation here is that there's been a lot of optimization in the large field case, but it seems that on the binary fields, there's much less space to optimize. Basically, the straightforward circuit is relatively closer to like the best possible optimized circuit would be my intuition. Okay. And with that, I'm ready to take questions.
Amazing, thank you, Matthias. Go ahead.
Can I ask a few questions?
Yeah.
Yeah, sure. So first of all, considering circuits to optimize, it seems like the natural target is integer addition, considering it's probably the main circuit being actually optimized in SHA-2 and Blake, right?
Yeah.
And my personal interest is integer multiplication. I think this is probably a good thing to know.
Is it like a 64-bit multiplication, or are you?
Well, you could do many things. You could do. I would suggest like 64-bit wrapping and with carry, like full 227 bits, I guess, and also maybe you could also check 256 bits because there is actually an instruction in EVM that does that. So it's probably a good idea to check how hard or easy is it.
Yeah. So I mean,
and I also have a remark that one of the reasons why Boolean circuits probably have less space in optimization is because this model is actually well studied. I guess a lot of people already spent a lot of time optimizing them. Okay,
and in particular, these hash functions are, I mean, also made so that they have efficient Boolean circuits, right?
Oh, sorry, another question. I think Kangaroo, about Kangaroo. I think you should compare hashes that have comparable capacity. So the compression that is able to compress similar amount of data. But Kangaroo, I think, has larger width. So maybe you should compare with Keccak 800, not Keccak 1600.
Yeah. It's a bit of a bad comparison because you're right. Like number of constraints per bits is not the same for each one of them. Yeah, I guess one interesting thing here is these hash functions are like very optimized for Boolean circuits. It could also be interesting to consider like higher level circuits that are not so easily optimized, like for instance curve operations and stuff like this.
Well, then we need to multiply numbers. First, we need to know how to multiply numbers.
Yeah.
And once we have multiplication, maybe we can think of a whole ISA like RISC-V. That would be very interesting. Thank you so much, Matthias. Great initiative.
I had a question about Blake 3. I'm surprised it isn't better. Maybe my mental model of the cost model is wrong. So this is flock constraints, correct? So it's the restricted R1CS. Are you finding that that restriction increases the number of constraints by a lot, because the Blake 2S, which is basically a naive implementation, we didn't spend much time optimizing it in Sapling, was 21,000 and something L1CS. And Blake 3 is, what is it, 7 rounds instead of 10? I can't remember. So I'm a bit confused, unless it's that flock restriction that is causing the large number of constraints.
I think what explains this is that we're kind of double counting. So in the R1CS, in the usual R1CS, you pay basically one cost unit for increasing the dimension and one cost unit for adding a constraint. So here you're paying both for increasing the dimension of K, and you're also paying for each row. So as K grows by 1, the other thing grows by 2. So this record, you can roughly divide these numbers by 2 to get, I think, what you mean by constraint.
Okay.
Yeah, it's kind of a hold up, a leftover from the general R1CS challenges over large fields.
I see. Okay, thank you. I'll have to look at the concrete efficiency of flock to see whether that's worth it.
Regarding alternative hash functions, in the past there has been a lot of designs optimized for hardware, and meaning that they also optimized sort of Boolean operations, not exactly Boolean multiplication, but something different. There were like a lot of hash functions also with very small state, like Spongent and others. So, and some of them even made it into standards, like lightweight cryptography standards, for example. Would be maybe interesting to see them in the benchmark.
Yep, I agree.
And Moro makes an interesting comment in the chat that if you have lookup tables, it changes the cost model, and we might see different types of optimizations.
Yeah.
Thank you so much, Matthias. In the interest of time, we have to move on. Sahil from snark.fast. The floor is yours.
Thanks, Justin. I'm going to do this with Gautam since he's the architect. So we're extremely excited about multiplayer auto research as a new way to solve some of these optimization problems across some of our frontier research cases. So I'll tell you more about it towards the end, but maybe we can just show you how we set up snark.fast, where it is, and of course, excited about solving some of the other, cryptography problems. So Gautam, do you want to share your screen?
Yeah, sure. I don't have much to share beyond what Justin presented. But yeah, okay, so we basically put together a snark.fast here. This is essentially just like a much stupider version of what ZK Golf is doing. We literally slap a timer around whatever the benchmark is in Flock's repo. Much thanks to Ron and Tamir from the Succinct team for helping us verify that the code was correct. And if you have a Mac, we have a benchmark here for Mac. You can click participate and paste something into your agent. We have a bunch of people here where your sort of agent is tracked. You can see how much people have improved things, and everything links out to a PR where you can see what everyone's doing. The agents sort of submit these really detailed, somewhat unparsable notes about what they're doing. And I guess we were supposed to be here to present that we had something for x86, but it's in the process of getting up right now. So please go to this page if you're interested, and if you have an x86 machine, it will be up in like an hour or two.
Thanks, Gautam. So maybe I can add a couple of other explorations, and then we'll open it up for questions. We'd love any feedback. I think one of the other dimensions we're thinking is there's a lot of collaboration that can happen once agents submit their notes on what paths and what approaches they took. And I think that is one of the interesting things that we're exploring. We're also doing some early experimentation with credit assignment, which strategy contributed how much towards the frontier metric. And I think those are a few new interesting things to kind of get more people to attack frontier research problems and the new metric is what is your token spend. for making progress, and what is the quality of improvements you can make. Also kudos to a bunch of people we're working with, ZK Security, Alex, on some exciting problems in the future. So please participate. Would love to have you guys join our solver network as well. We're open to any questions.
One more thing I'd add is like Justin had this slide at the beginning where he's like, now that we've got rid of Poseidon, can we also get rid of Blake? So there also may be an opportunity for adding even more, sort of seeing how much of our cake we can eat, basically.
Why would we want to get rid of Blake? Sorry, I'm not saying motivation.
Use SHA-2 instead, right?
Why?
I'm just a messenger here. You saw his meme.
Okay. Yeah. Good. Yeah. People like their government standards.
Yeah, that's a whole discussion for possibly the next Ethproof call. But yeah, SHA is just a little bit older, and it has more adoption. And if we want to build this a blockchain-wide standard, like and have Bitcoin play along, then that might be a strategic move. But again, no decisions have been made, and Blake is definitely awesome. Any questions?
Let the man write your hash functions for you. Yes.
Okay, great. I mean, there was a little bit of a hint here at working with Alex and ZK Security on something new. So great segue. I'd like to pass on the floor to Alex Hicks.
Yeah, thank you very much. Let me quickly share screen. Oh, I need to wait for the other one to stop sharing.
Goffin, would you mind stopping the share?
Yeah, sorry.
Perfect. All right, so this should work. So yeah, as was hinted at basically about a second ago, we have a new auto research thing which is coming. You can find the website is already online. It's better.codes. This will host an auto research project that is going to target the proximity gap conjectures. More specifically, we have a formalization in Lean of the contents of the open problems in line decoding paper that Dan, Giacomo, and Garth have written. This is formalization of both the grand challenges there, which is the coding theory part, as well as the toy IOP, which is also described there. It's all built on top of RClip, so we reuse the RClip formalism for the IORs, which we use to construct the IOP. We have a proof of soundness for the IOP, which is there as well. And very, very soon, you'll be able to then auto-research trying to improve the number of provable bits for the toy IOP over the sextic extension of Koala Bear with interleaved Reed Solomon codes. The bottleneck is currently my CPU compiling everything. That will hopefully go away very soon. And so we were hoping to get it launched in time and open for submission by this call. Most likely it will be probably a bit later tonight. But you can all start warming up, and it'll be very interesting. I think an important difference between this challenge and the ones is, of course, that people are going to submit proofs. The search space for proofs can be quite wide. We might see different techniques using different branches of mathematics. We've seen this so far on work in the conjectures, of course. Kind of last year, around last November, there were several papers that all had different proof techniques. So it'll be very exciting as a kind of different challenge. And I will also say we're starting with one challenge, basically kind of hopefully today. There'll be more challenges coming. We'll have the conjectures, restated for binary fields and other things. So this is very much the start, and it's certainly quite far away from the end. And that's it. Good luck to everyone.
Amazing. We have a question from Georg. To what degree is this more than just a way to donate tokens? I'd be super interested to understand how diversity in models, promotion techniques contribute to an overall better result.
So at least my impression from having participated in ZK Golf and Snarl Fast is that there's quite a big role still in kind of human expertise in guiding obviously the optimization direction that your model goes in, as well as finding new solutions. It's obvious that if you don't know what to look at, you're going to point Claude at something and it's going to just find some marginal improvement on whatever the current leaderboard submission is. With Snark.fast, I mean, we kept seeing even like 7% improvements when we were past 1.5 million compressions per second, which is pretty incredible. Token diversity is kind of token counts and model diversity, I think, is actually hard to estimate because some people have a kind of coordinator model which they use and which the submission originates from, but a lot of the work might be done by other models which are being orchestrated in some way. So that's not very transparent. And then I think promoting techniques makes quite a big difference. I'm very hopeful that actually from this proximity prize auto research that actually will probably generate a lot of maybe interesting lemmas and proof techniques that we can then upstream into ArcLib and suddenly kind of make available to everyone. And maybe, there's obviously proximity prize has a human element to it. The prize is split 50-50 between kind of peer-reviewed publications as well as this auto research prize. And it would be very, very cool if we could generate interesting content that then makes it back into kind of peer-reviewed papers and kind of informalized and communicated in a nice way. So it should be interesting. The other thing I would add is I think there's quite a bit of interesting scope for finding negative results or impossibility results. I played around with this with ZK Golf, where I was able to stop my model from going down stupid paths by instead having proofs in lean that some optimization wouldn't work or then generalize further than how it had been applied. And so kind of I want to think about how to encourage people to submit impossibility results as well and to kind of share these with other participants, since that seems quite interesting. And of course, when you talk about an IOP, you might have attacks and upper bounds on security, which this will definitely show up as a challenge as well on the website.
Yeah, we've seen very high correlation between the submitter, the human submitter, and the type of submission on other auto research challenges like ECDSA.fail. And one piece of alpha is that there's going to be an archive paper for the ECDSA.fail coming very, very soon, and kind of distilling some of the learnings about auto research in general, in addition to all of the quantum innovations that were brought to the table. Congratulations, Alex. I know you've worked extremely hard on this. And yeah, I guess it's coming either today, Friday, maybe over the weekend. And that's kind of the second auto research challenge that is landing, because we're also going to have the x86 challenge for Snark.fast. And one piece of alpha is that we're working on yet another auto research challenge, which will be probably announced during the next Ethproofs call. Great. So now we're going to start the binary fields presentations, and I'd like to give the floor to Ron and Benedict to talk about Flock, the recent breakthrough paper.
Sounds great. Let me share the slides. Can you see them? Can you hear me?
Yes. All
awesome.
Good.
Cool. So cool. So thanks for having me. Let me talk about Flock. I guess it was mentioned a little bit before as well. This is joint work with Benedict and William, which we only published like 2 months ago. So the starting point, at least for my end for this work, was I kind of from the theory side of proof system research, and all the way back in 2020, I was looking at this question of like very quickly proving correctness of Boolean computations. And we published this paper together with Noga on proving as fast as computing. And we showed that, for general Boolean circuits, which we were interested in because they're like a very clean theoretical model, we can prove kind of asymptotically as fast as computing, but this was hiding very large constants. And kind of recently with Benedict and William, we were asking, can we push this line of work into practice and actually get, something that is completely efficient? And what is kind of the fastest you can prove over a native execution? So the setting we focused on with Flock was the setting of sort of a batch computation. So we model the computation as an R1CS instance. Essentially, think of it as a Boolean circuit, and you're proving many of these. And maybe on top of that, you have some like minimal logic to connect like inputs and outputs. And for me, this is like a general setting of proving Boolean circuits, which I'm really interested in. But a particular application is for proving correctness of kind of standard hash functions, like Blake or SHA and so on. So we implemented this. We sort of did a lot of very heavy usage of AI for the coding. We rely on many existing ideas, which we combined, I think, in an interesting way, and introduced quite a few new optimizations on top. And I think we got some results that at least I was kind of surprised by which you can get the overhead for like single core proving over just native execution of the hash to be 250, sometimes even less, 200. This is on kind of consumer laptop from last year. And maybe a headline number is for Blake 3 compressions using the 10-core computer, you can prove over 600,000 compressions of the hash in a second, which kind of is pretty surprising, I think. This is purely the system itself is hash based. These numbers were based on SHA-256 for security. It is with 100 bits of security. Yeah. And we got sort of, I think, nice speed ups over other systems. These are numbers back from June. I know that Hashcaster has improved since, probably Beneath as well. I'm not sure, but it was kind of like quite fast. And that was sort of what we did in June, and I feel like ever since kind of there's a lot of energy around binary fields, and this talk is further evidence of that, and a lot of progress. So let me mention a few, some of which were already mentioned. So zk.golf, getting like smarter R1CS instances, snark.fast, crazy speedups using auto research. We'll hear later, I think, about GPU acceleration, and also Rahul will talk about this new his new work on AG skip using algebraic geometry, and Tamir and Eugene will also say more about x86 and CUDA variants. What I wanted to mention is a new version of Flock that we're sort of announcing today, which kind of is the next, I think, significant step with Flock, in which we were trying to like support new functionality and get like other improvements. So first of all, instead of just being able to prove a single hash, now we can prove many different hashes or other types of logic. All of these are connected using a machinery called the Jagged PCS, which we introduced with SP1 Hypercube last year. We support kind of a more rich wiring, which lets us like prove in general like circuits. This is via grand product GKR argument. We support now 128 bits of security, and we do this while actually still working with 128-bit field, except in the PCS, which kind of leads to better efficiency. And all of this is still without incorporating the AG skip and the snark.fast improvements. So I'm going to show you numbers. The numbers are only going to improve, and we know they're going to improve significantly. So in terms of like just raw throughput, if you use the new version of Flock just to prove Blake 3 compressions, even though we have all of this new machinery to support wiring and extra tables and so on, the performance has improved for 100 bits of security. And this is largely because we could, using the new architecture, we could leverage a better R1CS for Blake 3. And using 128 bits of security, we're getting not quite as good throughput, but quite good. And I think there's room for improvement with 128 bits as well. What I'm most excited about is that because we're now able to prove circuits, with Flock v2, we can prove our own verification circuit. And as a proof of concept of this, we implemented kind of a recursive hash chain, again, at 128 bits of security. So the idea is you want to prove a very, very, very large number of hashes. And what you do is you break them into chunks. Each chunk is like 2 to the 18 Blake 3s, let's say. For each chunk, you produce a Flock proof. But now you can combine these proofs in, say, a tree-like manner, and or IVC, and get eventually a single proof. And what I think is really compelling are the numbers. So each 2-to-1 compression, we can do it 200 milliseconds, again, on the same M4 laptop. And the proof size is 250 kilobytes. Just as a headline, with 100 bits of security, the recursion is 140 milliseconds. And again, this is without the AG skip, which will improve things, or the auto research. So just like briefly to say what our next step, or just like open questions, some of them are engineering, some of them are kind of more on the math side. So if we're able to, we know we can add the AG skip, and that should like speed up things quite a bit. Snark.fast is kind of crazy improvements, but we still need to see how we exactly digest them. And better proximity gaps for smarter proofs, faster recursion. And there, even within the Johnson bound, which some may think is a solved problem, getting better errors could greatly improve things. Second question that I think we're going to hear more talks about later on is even further enriching the functionality of Flock, doing some sort of either lean VM or a full-fledged RISC-V zkVM. There, a challenge is handling integer multiplication, which I think that Lev will also speak about. And lastly, I think one remaining place which feels to me suboptimal in the space is getting better lookup arguments. So that I think is something we'd also love to resolve. The repository is online. There's a branch called the Recursion Circuit, which has kind of Flock v2. And happy to take questions.
Wow, amazing. I had no idea about V2 and 2-to-1 recursion in 200 milliseconds. That is absolutely amazing. Congratulations, guys. So one question is, where can we look at the code? I think that's been answered. Any more questions? Feel free to just unmute, raise your hand, or ask in the chat.
You gave the proof size for 128 bits, which was 255K. Is it any smaller if you go down, or larger if you go up? How does it scale with the?
Oh, sorry, with the bits of security, you mean?
Yeah.
I think we should be able to get to if I'm not mistaken, to 200 kilobytes with 100 bits of security. I don't recommend going below. Are you asking about higher bits of security or?
So let's say I want proven security for post-quantum. So that is it 128 bits of classical security gives you 255?
I mean, okay. So if you're worried about things like, I'm not an expert on this. If you're worried about things like Grover search, then I don't think it's like.
No, I'm not worried about Grover.
Yeah, then I mean everything is.
But I'm worried about. Yeah, I am worried about proving things in the key ROM to make sure that.
Right. So I don't know what's the state of the art here. For me, when I should not have even said bits of security. I just need the maximal round by round soundness error of the protocol.
Right. Okay. All right. Yeah. I think that answers my question.
So I guess I have a question. Can you go to intermediate size between 128 and 256?
Yeah, I mean, and especially as you go to so the main thing that's most costly, we have this big gap, say for recursion, 140 milliseconds up to 200 for 128 bits of security. The main cost for this is that the correlated agreement error that we have from the 2025 paper by Eli and Ulrich and Swastik, kind of the numerator is not, the paper is amazing and it's a fantastic result that we heavily rely on, but it feels that the constants there are not as good as maybe I would hope for them to be. I think if you give me 110 bits of security, then you could probably have the same speed as the 100 bits of security, if that matters. But 120 is already kind of past what we can just solve with grinding with such smart proofs and fast recursion.
On the topic of proof size, I expect that proof sizes will significantly improve by next Ethproofs call. One piece of alpha is that Elon Yogev has a very significant proof size optimization that he's cooking. And I also expect that the better codes will provide some partial results. Part of the reason why I have this confidence is because we've already started, privately running the AIs on these statements, and they're already finding, new results, at least internally. So yeah, very exciting times from a proof size perspective. Thank you, Ron.
It is. I had an amazing experience kind of proving stuff with Claude, and it used 4 different areas of mathematics that I didn't know in enough depth to do this. Yeah, it's fantastic.
Yeah, and get ready for Rahul's talk later on, which will have some really hardcore algebraic geometry.
Absolutely.
Benedict, do you also have a presentation?
No, we combined.
We thought it wouldn't be too distracting to switch, though.
Okay, cool.
May I ask one more question if
of
we have
course.
time?
Yes.
So you mentioned that you looked at the proofs for Merkle tree-like construction and how to optimize that. But did you have a chance to look at something that is more of like a single chain of hash evaluations?
Yeah. So at two levels. So at the Flock v1 already, we had support for. So the basic system was just proving a bunch of hashes unrelated, but we also supported proving them in a chain with essentially maybe 1% overhead, essentially within noise. But that's like, it was somewhat tailored to the chain situation. In Flock v2, we have more flexibility. You can write down sort of a circuit involving these hashes. If you like write down kind of a circuit and treat it in a generic way, that introduces a little bit of overhead, but not too bad. And in particular, what I described with the recursion thing is just like proving a ton of hashes. So you can think of each leaf in the recursion as just proving an individual hash chain, and then the recursion is combining them.
Amazing. Thank you.
Sure.
Wow, Ron, I'm really speechless. I don't know how you guys move so fast. I guess AI plays a big role, but
absolutely.
Crazy times. Okay, next up, let me just have a quick look at the calendar. We have Jim, who will talk about Benius.
Yep, one sec. Okay, you can see Benius?
Yes.
Cool. Okay, so a lot of people on this call have probably heard of Benius, but as a recap, as of the end of last year, we basically rewrote the system as a new way to assemble the components with somewhat different goals from the original one. So this is Benius 64, which is the currently maintained and developed version of Benius. And the goal of it is fast client-side proving for zero-knowledge proofs, which has a lot in common with, but also is somewhat at odds with like massive, like infinitely scalable, high-performance building VMs. It's supposed to be efficient for proving classical symmetric cryptography. That's one of the big things that binary fields can deliver. And then aside from that, the goals are to have a simple, secure platform with good developer experience to build these types of privacy-preserving client-side applications. So some examples, the very first one we built that was driving development is ZK Login, which is, or a copy of it, that's the name of a paper that does zero-knowledge proofs of RSA-signed JSON web tokens. Another example is the type of hash-based signature aggregation that the lean Ethereum project is planning on. And another recent application or demo is BIP32 Bitcoin address derivation, which is a collaboration I did with Project 11 that is sort of a potential solution to the Bitcoin post-migration problem. So these are the types of applications that we want this library to support. The computation model is not Boolean circuits, but it's very close. It's circuits over 64-bit words. And the computation model allows for a pretty rich set of gates that you would naturally find in instruction set architectures and such. So bitwise and or XOR, bit shifts, both 64-bit and 32-bit variants, integer comparisons, select, and then there's a special ghash multiplication instruction and a specially accelerated integer multiplication instruction, which is not listed in this. And then the computation model can have non-deterministic hints. So these are computations that are not, that you must constrain yourself, but will derive some values from some other values. So this is a circuit model, not a VM. Circuits don't have branching, and they don't have writable memory, but despite that, it's still a very powerful model and very simple to build a protocol around and use, and is fairly low overhead. Oops. Okay, so the new thing that has been in progress for the last 2 months or so is a multi-chip architecture, and this is somewhat prompted by, or in large part prompted by the numbers that Flock was able to get. The biggest, or one of the biggest causes for the Flock Binia 64 performance gap is the expensive wiring check that you incur when you have a monolithic circuit. That was actually the dominant step in proving time. And it also made verification very slow because the verifier needs to know this entire wiring circuit and do it. So Binia 64 now supports a multi-chip circuit architecture where you can write subchips with data parallel subcircuits, which is something you see in, I think, Phalanx originally, but Flock, Jolt, etc. And then we have a primary single instance circuit, which takes in the statement and sort of dispatches these chip calls, and the chip calls can be arranged as a acyclic graph of calls. This almost completely eliminates the wiring overhead for proving and verifying. And so there's one caveat. The feature is almost complete, except that it does not yet constrain that any of the chips are talking to each other, but I think that's a fairly small thing that shouldn't affect the proving numbers that you'll see in a minute. So that's coming very soon. Here are chip benchmarks. I hate benchmarking competitor code bases because I don't really know what's going on, but on the AWS Graviton instance that I've done all my benchmarking on, the numbers deviate pretty significantly from what you see in the paper, so I wanted to put this for comparison. These are 3 hasher benchmarks. The proving time is worse than Flock by something like 20 to 30% in most cases. I think Ketchak's fairly competitive. Witness Gen has some issues that could be improved on, but the proving performance has gotten a lot closer than what was shown in the Flock paper. This is based on the Flock main branch code base, so if there's more improvements that are new, then this doesn't incorporate that. Oh, and then one thing I wanted to add is that we have a library for SecP256K1 point addition, which is just to demonstrate that there's an int multiplication accelerated protocol in Binia 64 that's really powerful for the types of things you might actually want to prove in a zero-knowledge proof. As a case study of the multi-chip architecture, we implemented XMSS signature aggregation. So the statement is something like you have n signers signing a single message. Their hash-based signatures are the witness data. And then the architecture is you have a tiny glue circuit that dispatches chip calls to the XMSS verifier, which dispatches chip calls to the core, the hashing core, and can basically do something like 500 XMSS verifications in a second based on Blake 3 and otherwise a specification for this that is in the Ethereum Lean B code base. And then the last thing is the Binius library is developed to be fairly modular, but also opinionated, but there's a lot of batteries included. So there's lookups, there's a ZK wrapper proof. It actually, you can run proofs to be either ZK or non-ZK, and recursion is very close, but not done before this call. And when I say we, this is the list of people who have been contributing recently. Many thanks to Thomas for a ton of really good work here, and Wilson, Latif, Paul, and Project 11 for working with me on the BIP32 thing.
Amazing. Thank you so much, Jim. Benedict asks, how does a SecP256K1 scalar more compare to a hash function invocation, e.g. Blake?
Let's see, let me go back to the benchmarks. So we could do 16,000, around 16,000 EC point adds per second, and Blake was getting something around to the 17, 128,000 per second. Yeah, something like that. So they're slower by a factor of 8-ish.
So that's a scalar addition.
Wait, no, a point addition between 2 points.
A point addition, okay.
Point
so
addition.
Scalar,
Yeah.
so yeah, point addition.
Yeah,
so scalar mole is even
faster.
Like,
wait.
No, the gap is bigger. Like it's like if I prove, let's say, proving one hash function versus proving one scalar mole, it's like 800 times faster. I can prove 800 hashes while I can prove one scalar mole, right?
Depending what scalar mole algorithm you use, yeah.
The library has a fairly sophisticated way of doing sec-p stuff, so it does the endomorphism trick, and also it does Strauss for multiscalar multiplication. So for things like BIP32, you can it's not just sort of 256 point additions to do a few scalar moles.
Mm-hmm.
Jim, a quick question from me. So within the EF, we kind of have LeanVMB with Emil. We have Thomas spending a lot of time helping with Benya 64. And there's like all sorts of other kind of parallel efforts. Do you see an opportunity to have some sort of equivalent of Plonky 3, maybe Plonky 3B or some other name for binary fields?
Yeah, I mean, that's really what I hope Binius could become. So, I mean, to comment on, I don't necessarily think that the Binius 64 circuit model is going to be the best for, building a RISC-V VM or something. You get efficiency from doing the Boolean circuit with massive data parallelism. The 64-bit model is meant for circuits, but I think there's a lot of high-quality code in the Binius code base, like a portable multi-architecture field library, and it would be possible to build, more and more sophisticated binary field protocols using some of the components that are in there. So if people are interested in helping drive Binius into that direction, talk to me.
Maybe I can also mention that in Flock we borrowed some of the Binius code and really appreciate both the code, also the research papers. So.
Oh, sorry. One thing I did want to mention also, I'll drop a link, but there's a binius.xyz website, but also binius.xyz/spec.pdf is a fairly complete protocol specification, which I think is really important for cryptography protocols to actually say what they're doing.
Absolutely. Repeat that URL.
binius.xyz/spec.pdf.
Okay.
It's fairly up to date. It still needs the multi-chip architecture stuff, but yeah.
Amazing. Thank you so much, Jim, both for your original ideas in 2023 and persevering all the way up to now, and so much potential for Binius 64 potentially as a library. Next up, we have Srinath, who will talk about binary Spartan.
Okay. Let's see.
And I believe the paper has been submitted to ePrint several days ago, but they seem to be on holiday at ePrint.
Sorry, I'm facing some issue with sharing. I may have to rejoin because I had to change settings.
No worries. See you soon. In the meantime, let's move along with Rahul, who will talk about fast binary zero check using some fancy algebraic geometry.
Hey, hello everyone. Let's see. Let me just share. Here we go. Okay. Sorry, spoilers. Okay, right. So I'll be talking about a new sort of gadget called AGSkip, which is the point of this is to optimize the round skipping in binary sum checks. So let me start with the sort of overview of what the problem binary sum check round skipping is trying to solve. So this is a sort of technical optimization to the sum check protocol when you input data in a small field. And the problem here is that the sum check protocol, it needs to work in a very big field to achieve soundness. The sort of challenges you draw in every round, they have to come from like a very big set, and you need to use this thing that a polynomial doesn't have too many roots, and so on and so forth. So very roughly, this is not like 100% accurate, but you can think of it in this way, that the first round of sum check, basically it takes about order of data work over the field in which your input data is. However, the later rounds, basically they take 2 to the negative n times O of data work over the bigger field that you need for soundness. So if you compute this out, what you can say is that rounds sort of 2 to whatever end up being extremely expensive compared to your first round. So the trick people normally use is that you want to find a way to increase the work that you do in round 1 to sort of skip these like very expensive 2 to whatever rounds. And in 2013, basically, Mir found a sort of abstract formalism for how sumcheck works. That the way you can do this round skipping is you can find a certain kind of error correcting code over your big field with message length to the power of the number of rounds. And if this error correcting code has the right properties, this lets you skip n rounds. So right, it needs to satisfy certain unusual properties that maybe you don't ask for normally in the theory of error correcting codes. But it turns out that there's a standard choice you can make that you can use Reed-Solomon codes, and they satisfy all these properties. And putting these two things together, you get something that's normally called Gruen's trick or univariate skip. Okay, so that's the problem that we're trying to solve. We're trying to do this technical optimization to sumcheck. We reduce it abstractly down to finding a particular kind of error correcting code. Let's talk about the kind of error correcting code that we need. So here's the property that the code needs to have. So basically it's something called multiplicativity with a few bells and whistles. So what is multiplicativity? Multiplicativity means that we have an error correcting code C. There exists a product code that will denote C star such that, well, if you have two messages of C, then you can sort of multiply them together to get a message of C star satisfying a few properties. So if you encode the two things of C and you take a pointwise product, that is basically the encoded message of C star. So this is sort of the important, like the core thing of multiplicativity. And the other part is that when you take this product on the message side, not on the code word side, the prefix of that is basically the pointwise product of your messages. So putting these two things together, this is the thing that lets you do like nonlinear sum checks. The next thing you need is that C star has extremely large minimum distance. And this is basically for the first round challenge soundness. And the last thing you need is that this is sort of where the optimization comes from, that if you start with two C messages in your base field, F2, then when you look at their product, the entries of that are in some small field F2 to the K for some small K. So we are going to achieve K equals 1, which is where most of the improvement comes from. Reed-Solomon codes give you K equals N. And this is where the optimization comes, so your first round can be over F2 to the K instead of F2 to the 128. So if you look at how the work works in sumcheck, basically the thing you want to minimize is this field K multiplied by the dimension of C star minus the dimension of C. And however small you can make this number, that's how efficient your code skipping ends up being, your round skipping ends up being. There's a sort of second optimization, but this value K times this difference of dimensions is sort of the main thing that you want to optimize. Okay, so basically like the point of this work is we find a code that makes this much smaller than the Reed-Solomon value. Okay, so we find this code using algebraic geometry, and there's a particular construction called differential Gopa codes. So how does this construction work? Well, the first thing we're going to do is we're going to choose a system of polynomial equations in D variables that has greater than or equal to 2 to the n solutions over F2. And the solution needs to basically be one-dimensional in some technical sense, the system of equations. So then you can bring in the algebraic geometry input. So if you satisfy a lot of technical properties, if X satisfies enough technical properties, then what you can do is you can take X and you can produce two vector spaces of rational functions L1 and L2, and you think of these as functions on the solution set of X, and these two vector spaces of rational functions are going to satisfy some properties, and these properties are sort of going to line up with the properties of the code that we're trying to satisfy. So first property, if you have two rational functions in L1, then their product is inside L2. And the second two properties are basically interpolation properties, where if you take a function in L1, it can be interpolated from the evaluations at 2 to the n, at the 2 to the n f2 points, f2 solutions of this system of equations x. And if you take something in L2, it can be interpolated from these evaluations and basically a bunch of derivatives that you add on top of these evaluations. These are just rational functions, polynomial divided by polynomial, so you can take derivatives. And just like you can interpret univariate polynomials from evaluations and derivatives, you can evaluate these rational functions from evaluations and derivatives. So the algebraic geometry input is basically, it checks all the technical conditions and it gives you this input. So how do we get the code from these two vector spaces? So C is basically going to be an interpolation code. Your message is the evaluations at these points, encoding is interpolate, and then you can evaluate at the big field solutions. C star is similarly an interpolation. And in this way, this product map is you take your two messages, interpolate them, evaluate the derivatives to get the C star input data, and then you can multiply those derivatives using the product rule. So these are all very simple things. And if you do the cost accounting here, basically your cost comes from optimizing dim of C star. Okay, so the explicit construction was done by AI. We'll focus on skipping 6 rounds, so 2 to the n is 64. The next algebraic geometry input is that the dimension of C star is determined by a invariant effects called its genus. So the goal is you want to find the lowest genus X with 64 solutions, compute the explicit L1 and L2 using the algebraic geometry inputs, and do the interpolation maps. So the last generation of models can do this in a weekend. I really want to emphasize that this was a project that was seriously unlocked by AI. This would not have been practical to do without LLMs. This would have been a months-long computation requiring experts in this very specific field of algebraic geometry, which none of us are. And the key point here is that you have the complicated math construction, but because everything is worked onto explicit matrices and polynomials at the end, and the properties of the code are very combinatorial, once you've constructed everything, you can check that your code is valid by scripts and elementary math. You can completely forget about the algebraic geometry once the construction is done. So you have easy verification, and this is very important for anything you generate with AI. So how well does the construction work? Well, basically this optimization goal is about 158 versus about 380 for Reed-Solomon. Even better, you work over F2 instead of F64. The arithmetic is much more hardware friendly. And overall, you get basically a 2x speed up to the zero check part of the flock protocol, which I think is the main bottleneck.
What is the genus of the result?
The genus, it's 95.
What?
95, yeah.
Okay.
Yeah. Yeah, sorry, is that crazy? Yeah. This is why you need the AI to do all the computations for you, because it's very
well, okay.
Yeah. So this is yeah, so I think this is like a
no, it's more like surprising that there are this such special curve of genus 95.
Yeah, it's amazing, right? Because of
like with
yeah.
Okay.
It's a small point thing. Like the linear factor asymptotically is much worse, but apparently 64 is small enough that you can beat that linear factor. And you can do this with a genus 95 curve.
So can you find similar curves also for higher characteristic fields, or is it specific to characteristic 2?
It seems like a general sort of special thing. There's a website, Manypoints, you can look at, manypoints.com, where people have been trying to track records of sort of low genus curves with lots of points. So you can see there that there's a result that says that asymptotically, as your genus gets very high, the number of points is some linear scaling of what you have. It's upper bounded by that. But if you look at that site, you can see that for it takes a long time for that asymptotic to kick in.
Mm-hmm.
So yeah, this is an entire field of like math that people have been working on very hard, and it's yeah, it's very nice that they did all that work already because that's what the AI was able to take advantage of to find a new curve with 64 F2 points. Yeah.
Rahul, have you submitted a paper on ePrint for this?
No, this is not submitted yet. So for embarrassing reasons, basically, I wrote a draft and it was not readable to people in coding theory. So I think Ron and Tamir have a version that's fixed up that should be there next week. Hopefully, we'll see what happens. Yeah.
I think
Amazing.
Just then regarding your question, I think one thing that's, as I understand, of F2 that's nice is we're anyway implementing, like for over Reed-Solomon, we anyway implemented the FFT using a matrix multiplication. So essentially just lookups. And with the AG code, it just becomes a different lookup that's in fact even more efficient because exactly of what Rahul has here on the slide. I think once you get over larger fields, it's not clear to me that sort of the same matrix multiplication, like then maybe you pay for this quadratic cost. Like this doesn't actually have a fast encoding algorithm, but we don't care.
Yeah,
I see.
But over larger field, you probably don't care that much about that. Like you can use normal univariate skip, which already has optimal properties if your field is at least like what basically 2 to the power
the
size.
Skip length, yeah, that's true.
Amount
Yeah,
of rounds that you want to
field,
skip.
yeah.
Yeah, you don't pay much of a cost if your input data is in a bigger field. This is, yeah, binary is sort of where the benefit is biggest because like the soundness field is so much bigger than the base field.
Thank you so much, Rahul. This is fascinating. We have many questions in the chat, but in the interest of time, let's move forward. Anyone who has questions, if you go to the agenda on the Ethproofs community call, there's a link to Rahul's Telegram handle. So you can just DM him with all your ideas, and hopefully that will lead to fruitful collaborations. Srinath, do you want to try again?
Sure. It's better this time. Okay. All right. Can you guys see my screen?
Yes, perfect. Thank you.
All right. So I'm going to be talking about this binary Spartan. It's not a new proof system. It's just Spartan over binary fields. It provides transparent proofs. Proofs are polylogarithmic, plausibly post-quantum. There's a short note about this work. It was submitted last week, so it could be public anytime. Just a quick recap on Spartan. Spartan is a proof system from 2019. It's a snark for R1CS. It's generic over a multilinear polynomial commitment scheme. And in prior works, it has been instantiated over different commitment schemes like group-based, lattice-based, also hash-based. It also works for both types of fields, prime fields and binary fields. The proof system itself is lean and fast because it only commits to the witness, runs 2 sum checks, and produces a proof of the witness polynomial at exactly 1 point. So one question that I had was, what happens if you just do an implementation of this scheme over binary fields? So here is one slide that depicts the performance of such a system. On the left, there is throughput on various standard hash functions. On the right, we depict latency of proving a single hash function. As you can see, just doing a implementation of known techniques, we can already get past 200,000 hashes per second for SHA-256 and cross 400,000 hashes per second for Bleak3. Even on the latency, you can see that it's significantly faster than many other schemes. In fact, it's the fastest scheme in the client-side proving benchmark of Ethereum Foundation. So what did we actually build? So here is a single slide that depicts the scheme that was implemented. So we have the Spartan protocol, and we instantiate this with the Ligero polynomial commitment scheme. And then we implement 6 optimizations. And all of these optimizations are widely used in the literature and also in many implementations. In fact, 5 of these 6 were developed in the context of prime fields, and 4 out of 6 were developed in the context of elliptic curve snarks. And nearly all of these optimizations are present in modern Spartan implementations. For example, Spartan in Jolt implements 5 out of those 6 optimizations. And here is one slide.
Oh, Srinath, we might be losing you. Let's try turning off your video.
So, how this performance that I showed other.
Sorry, Srinath, we can't hear you. We're losing you. Let's see if it gets better within the next few seconds. If not, we can move forward to Andrija. Cool. Yeah, let's just move forward. Andrea,
Yeah.
Are you ready?
Yeah. If we don't want to wait for him to reset, I can jump in.
Let's see if he's back. Yeah, let's just go ahead.
Yeah, sure. So I'll be speaking about both Ligerito and Bolt. So it's gonna be two presentations in a row from me. Let me just share the right screen. You should see this, right?
Yep, perfect.
Okay, is there a wait presentation? Yeah, okay, wait, sorry. Okay, so this is my joint work with Guillermo from 2024, 2025 actually. So I'm gonna talk a little bit about the scheme. So we're gonna look how Ligerito was developed, what's the core idea, what we published first, how we used binary fields back then, and also since we had like a lot of questions, what is like comparison with Weir, what's the relation, what's the difference? I'll just try to cover some stuff that I know. If anybody knows anything else, feel free to jump in or send the more resources. So I think the audience here is like good enough, so we don't need to go through what is like a multilinear PCS, but the idea of Ligerito was to build a state-of-the-art multilinear PCS that was quite agnostic. So it was not depending on any linear code. It was not depending on a finite field. So it was like quite generic. Okay, so I think the main idea of how Ligerito works is that it's literally, you can imagine it as delegating Ligero verifier and having this like recursive protocol, having like doing it enough time before the instance becomes too small, then we can just send it. So how Ligero in general works, so we have some data matrix. We pick like some linear code and we commit to the columns of these matrices. Like we commit to rows of this matrix via, for example, Merkle tree, and some hash function we like. And then verifier sends some randomness. And for the multilinear polynomial commitment schemes, this randomness is not just any randomness. We are forming this like EQ vector, and then we are essentially doing a matrix vector product with this. So what really happens in this protocol is that verifier then queries, given like the security we care about, queries some of the rows of this committed matrix, and then it checks a bunch of inner products. So Ligerito and its core, you can just imagine this as a variant of code switch, where essentially what you do is instead of sending M to the verifier, and then verifier is like doing this inner products. We are delegating this to the prover in a new round. So prover then, instead of sending M, it commits to M. And here is the nice property. It can pick any dimension, how it wants to commit to the new message, like this new like folding, whatever dimension. It can pick different code, different rate, whatever it commits to it. And then we run one recursive instance to check this now Ligero, or like another recursive instance of Ligerito. And then there is also like a bunch of these sum checks that we have to prove, and we can batch them all together. It works very nicely. The one expensive check would be to delegate proving hashes, or it was before flock, but essentially you can leave verifier doing a few very fast hashes, and then delegate the inner products. So then if you want to make Ligerito succinct, is happening, sorry for this. If you want to make Ligerito succinct, you need somewhat structured code. So our implementation and what we were targeting back then was like read Solomon codes and over binary fields, but that doesn't matter for this part. So using any like generic linear code, the verifier would be linear. There is like a structure to exploit, which is given the EQ vector, which is a tensor product of this like vectors of like length 2. If the row of the generator matrix of code you use can also be written as a tensor product of these small vectors, you can actually compute this product in logarithmic work. And if you think about what is the last step of the checking this sum check, it's actually like evaluating polynomials in a random point. So the hard part for the verifier is to evaluate this row treated as like its low degree extension in a random point. When this row is structured, actually verifier can do that in logarithmic time. If you want to, for example, use some other code, you can also imagine having like another snark where you just delegate this, like again, linear work to the prover, where, I don't know, if you want to use RA code or some other code, you can also have a specialized snark doing this for the verifier. So the protocol itself is very modular. You can do this for like both over like additive and multiplicative fields for Reed Solomon. And yes, what we first did, I'm super sorry about this. What we first did in our like implementation that is now like ancient in terms of what are the speeds and what are people doing with the AI and all the optimizations, we were anyway, even then, very bullish on doing these things over binary fields. And we were trying to just demonstrate that we don't need all these GPUs and that we can have like a very efficient snarks running on CPUs, client side, and consumer hardware. So the whole point and why are we here now is that we have this like CPU instructions that are very efficient to handling multiplication in binary fields, and additions, as we know, is just XOR. So as I maybe mentioned, Ligerito is again coming as a very flexible protocol. So each recursive step, you can pick a different dimension for folding. If you're always using the same code, it can still be like different rate. And you can also just be creative and pick different code as you're recursing through dimensions. And then what do we know from like relation and what happened with like with Weir? So like original Weir paper, if we understand it correctly, it was way more like algebraic in nature. It was type of a code switch, but it was like curated to just use the prime field Reed Solomon. And then literally, if somebody's here, maybe I forgot, but literally like a few days before we published the paper and implementation, there was also a PR made in Vir repository starting to mention interleaved codes. So at this point, I don't know, but like when I spoke to Giacomo, seems that we are now like converged to having like essentially the same protocol. But I think that these two things were developed from like a very different ideas, and it was just interesting to think about which perspectives we took. So yes, again, if I said something wrong here, feel free to stop me and point to other stuff. But I think that there was like I think 2 days before we published or something like that, the PR starting to mention interleaved Reed-Solomon codes in Vir repository. And yes, also as this call is like very oriented towards Flock, I'm very happy to say that the current implementation uses Ligerito that we have for Flock system. So yes, let me know if you have any questions, and then I can jump on the other presentation.
Andrea, we are very tight on time, so my suggestion would be to just go ahead with the next presentation.
Okay. Yes, sure. This is on the other paper we had called Bolt. So my share screen is now not working, right? But it was just working. Sorry about this. Let me just try to reset everything. Sorry, I know we are tight. Share. Yes, now it should work, I think. Okay. And sorry for this presentation mode in Google Chrome is not the best. I thought it's better. Yes, it's not working. Okay, so this is a work I had with Kobe and Ron, who I think are both here. So I just said we were having this work called Ligerito, which is multilinear PCS, and Bolt is another multilinear PCS, which was trying to optimize this further. So again, we all know what is the multilinear PCS here, and I'll try to make this presentation faster. So what we saw with the years was that Reed-Solomon codes were very efficient, very nice to handle. They have these beautiful structures that we can exploit to have succinct verification, very efficient code switch, etc., etc. So the only kind of drawback of Reed-Solomon is they're like n log n. So we were trying to see, is there like something we can do to exploit some other codes that are faster and not sacrifice everything else around it by much. The most obvious thing that suffers is proof size, as we can see with like breakdown and other schemes, but also something very not trivial when we want to implement this in practice are these evaluation proofs. So how do we code switch, or how we even prove the statements about these different codes? So literally the goal was, can we make something like faster, significantly faster than just pure Reed-Solomon, but not just sacrifice everything other. So we have this thing called sketched codes. So it's like a very like easy thing to imagine. So if you can imagine having like some very sparse matrix, which if you want to encode with this matrix, it will take linear time, or something that is in complexity of number of non-zeros of this matrix, or its weight, however you call it. So essentially what we do is we use this systematic code where we first encode the big message that we have with this sparse matrix, and it takes something, let's say, like purely linear time, and then whatever is left to amplify the distance of the code, you can apply any other code you want. This can be some other linear code, or as you will see practically, we then, on this smaller thing, used Reed-Solomon. So the idea of this work was to try to make something as practical as possible and not like think that much about the big O notation, so to say. And the intuition here is very easy. It says if something, if the like initial message is of highway, we are good. If not, then encoding this with like one matrix and then amplifying it with the other code will give us some okayish distance. So what are these sparse matrices? So we have something called LDPC codes, or like low density parity check codes, which are codes which parity check matrices are dense, are sparse, sorry. So what you can actually do here is you can use these parity check matrices as an encoding step in the first time, which might be unintuitive at first glance. And they have like a very nice property, which is that there are no low weight messages in the kernel of these matrices. So this literally gives us the property that is nice for distance. If your message is good enough, like have a high weight, you're already good. If it's too low, then encoding or like multiplying it with this parity check matrix will be non-zero. So then the other code will take care of the distance. So what we practically did, we had this 8-factor compression, and then we used 1/2 rate Reed-Solomon code. So you can imagine that on a big instances, you're doing 8 times smaller n log n operation with rate 1/2. And the first thing is linear. So why are binary fields very important here is that when you start thinking about how these LDPC codes look, they are sparse, and you can do like a lot of like things in parallel with like SIMD and put things very nicely into cache and use all the CPU instructions. So if you don't have all of this like nicely implemented, it's not that obvious that this is like a significant implementation. So I think that Kobe did the most amazing work here, where we actually did like a far stretch to show that this is actually practical and that you can do a very nice and efficient implementation of encoding with this LDPC code in the first step. And for the best kind of parameters, we also used 32-bit binary field. You can have this over other fields, even just binary field, with like some pure additions. So these are some benchmarks for like a few months ago from the paper we published. By now, I think people would really be able to even more optimize on that. But this is just how it was now. So on like M4 max, we were literally able to get 2 to the 30 commitment time over 32-bit field in just like a little bit above 1 second with 2 megabyte proofs. And we are very, very optimistic that this can be pushed even further with more smart tricks in optimizing around cache and SIMD and all other CPU instructions. So this gives like around 4 times improvement over Reed-Solomon implementation, also over binary fields we had then. And one thing that people will mention, like will see, is that in the pure unique decoding radius, the proofs are still quite like large. So either there is like some potential way to recurse this, or there are like other things that we didn't yet have time to explore. These codes come with some very nice properties that should not be a part of this presentation, but you are either ask me questions or look in our paper. But also one of the very interesting open questions is that there are now these new papers showing that we have proximity gaps up to capacity for LDPC codes. So if we can figure out the parameters and how to do this, what is the regime, we can actually significantly lower the proof sizes and be like very close to pure Reed-Solomon code maybe, but like sufficiently faster proving time. They also come with like a very nice evaluation proofs. But yeah, this is for some other time and a longer talk. That's it from me.
Amazing. Thank you so much, Andrija. And yeah, very interesting design space to look at alternative codes. We are very much in a rush, so let's move ahead with Lev, who will try to resolve one of the big outstanding issues with binary fields.
Well, okay, I was told that presentation should be quite short, and it is also non-technical. I'm sorry about that, because I did not understand that it can be technical. Okay, anyway, I will share my screen. Just a few words. So basically, my opinion is word computer should be able to multiply numbers. I know it's a bit controversial, so I will try to justify this opinion. So first of all, characteristic two protocols are excellent at Boolean circuits, but arithmetic operations are, especially big-int multiplication, is slow. And currently, Ethereum has notable amount of arithmetic, like as it stands right now in signature validation and BN opcodes, and it will not instantly go away. And moreover, just like there are contracts that use a recover, they will not instantly go away, even if you transition layer 1 to fully post-quantum something that only uses hash signatures. And moreover, future protocols might need to multiply numbers too. Like lattice-based protocols, for example, do need to multiply numbers in like even quite like moderately sized integers. Anyway, multiplying numbers is important. That's my thesis. Okay, so there is field switch protocol. There is an unfortunate collision with ring switch, but basically the idea is essentially the same. You commit to data over one field and simulate opening over another field. Important is we want to lift the characteristic. So we commit to the data over a specific choice that I made is the commitments are over f2 to the power 127, and we reinterpreted them as elements of fp, where p is 2 to the power 127 minus 1, which is prime. So basically, we want to evaluate a polynomial over this fp in a point, a multilinear polynomial, and we want to simulate this process. And it turns out it is cheaper than doing arbitrary multiplication because when you are evaluating a polynomial, you are basically multiplying many elements by the same number. Like you pick the right half of the polynomial, multiply all the elements by the same number. Then you fold, then you repeat the process, right? And so lookup-based computation in the exponent suddenly becomes much better. So this is the observation. So, okay, I have one slide about theoretical performance. Here is the link. I can also copy it in chat, and it is in the group. So there is like description of the protocol. It's not published in ePrint yet, but like at some point it will be. So commitment costs, if you want to transfer n elements, you need to commit to n divided by half more full 127-bit elements. So for example, if you want to transmit 64-bit numbers, which is reasonable choice, you will pay like roughly double the commitment costs. You will also need to commit to some lookup star tables, but they're small. And lookup costs are indexed by limbs of the committed data. So basically, all your committed data is split into limbs of some reasonable size. I don't know, in current implementation it's 16, but it could be larger. Basically, you need to do a lookup star indexed by these limbs. Okay. So I have a fully vibe-coded implementation. Verifiers are kind of, sort of like I read them, and they were obtained by like sort of walking AI through it, but they're still far from being like written by me. Prover is not written by me at all. You can find it by this link, Morgana Proofs, fields, which just remember to move the dash between S and W. So currently on my machine, which is x86 32 core. It does measly 3 million per second, which is full 127 bit elements, which is, I think it's too small, but there is like a significant room for optimization left. So that's it. If you have any questions, like this performance is probably already enough to justify it, like for usage for like big arithmetic, if you need to do something with 256-bit numbers or whatever. But I think this probably can be improved a lot.
Wait, that's 3 million. What is 3 million? What? Sorry, I didn't.
127-bit. So basically, this is like full argument, including commitment, ring switch, and like all the rest, which like commits to. Well, it commits to 1 million.
But can you formulate it? If I want to do 64-bit multiplications, is it 3 million 64-bit multiplications? Or
it will.
like how does this translate?
I think it will be 1.5 because wait. First of all, it will be a bit cheaper because I'm transferring full. If you want to do like native field 127-bit multiplications for some reason, you would have 1.5 million of those per second with the current implementation. I think it's too slow. But yeah, it's probably not that optimal. At least theoretical count seems to suggest it probably should be faster. Some message. Okay, it's not stopped. Yeah, okay. And generally, biggest bottleneck that I observe is lookups and the fact that you are going into exponent at all. So I think very useful thing to do would be trying to benchmark it against like, let's say, naive flock circuits and checking whether maybe you could avoid maybe you could avoid going into exponent and seeing this element. They're not witnessed, so they're not committed, but they're still in the IOP.
Thank you so much, Lev, for sharing these ideas. And I know that Benedict is also kind of shared with us privately that he's looking into this design space. So the two of you should maybe chat even more. Next up, we have Emil, who will talk about LeanVMB, the binary version of LeanVM.
Thanks. Hello, everyone. Can you see my screen?
Yes.
Okay. So LeanVM is this minimal ZK virtual machine whose goal is basically stacking Ethereum, so aggregate hash-based signature, post-quantum data availability, recursion, etc., etc. It's a minimal ZK virtual machine inspired by Kero, and it was previously using Koala Bear and Poseidon. And I'm going to speak about the transition to binary fields. So as a quick reminder, there was this read-only memory, two registers, frame pointer and program counter, a very limited number of instructions, and so the field was Koala Bear, extension 5, and Poseidon 1, and the security was approximately 124 bits. And thanks to the recent breakthroughs in binary fields, we've been able to move it to binary fields, keeping essentially the same virtual machine in the sense that there are still two registers, still read-only memory, still a very limited number of instructions, but the field is no longer Koala Bear. It's either a large 192 bits extension field for the memory values, let's say, and the rest is in the 64 bits binary field. The hash function is Blake, currently Blake 2s, but it doesn't matter because in some sense the key point is that we can basically use standard hashes, and deciding which standard hashes we are going to use, it's still an open question. and the security is 4 bits better than previously at like a standard list level 1 security. In terms of performance, it's essentially close to the because it's very recent, so less than 2 months, and performance is progressing quite fast. So hopefully we will be able to get the last 2x that we need to target above 1,000 XMSS per second and below, let's say, 250 milliseconds for 2-to-1 recursion. And in terms of hash proving, we are below the Flock 700K Blake 3 per second because we use Blake 2S, and more importantly, because we use a bigger extension field to be in the list decoding regime to get small proof and easy 128-bit security, even though given like the new Flock 2 version, we may have again improvement on this. In terms of proof size, using a big 192 bits extension, we can get the same small proofs as the previous version of LinVM. So I think between 200 and 300 kilobytes. And hopefully with the proximity gaps conjecture, when they will get solved, we will be able to have sub 100 kilobytes proof size for hash-based snarks, which is amazing. Quick technical details. So as I said, we don't use ghash because like the list decoding regime is quite good to use to have small proofs and to trivially have 120-bit security. So we use a degree 3 tower extension over a 64-bit field. And the key idea is that there is this, we fix a multiplicative generator G of the 64-bit field, and all the arithmetic of the VM is in the exponent, meaning the memory addresses, the program counters, etc. It's not 0, 1, 2, 3, 4, 5. It's 1, G, G square, G cube, etc. So it's kind of a trick. And the idea is that using this, you get a cheap way to express memory shifts and offsets. You transfer addition to multiplication, which you can do very easily. And so you get roughly the same speed as before using Collabere. So as I said, the hash Blake 2S currently proven by Flock, ring switching from the 1-bit field to the 64-bit field, because we commit in the 64-bit field with WIR, aka Ligerito. Permutation is handled by GKR Grand Product. And for the lookup, we currently use a nice idea, essentially offline memory checking in the exponent. It's nothing new. It was described by, I think, the original BNews paper. And there is a nice BNews blog post that basically explains that if you have some kind of memory bus that you can implement with Grand Product easily, you can build on top of it a lookup argument that has the advantage of avoiding to commit twice, meaning you avoid because if typically there are some lookups where you need to commit once, samples of some randomness and recommit. And in the end, when you open, you have to provide Merkle openings for all these commitments. And so you pay a bit in terms of proof size. So I like this. And also like this lookup is very simple, so it's kind of nice, even though it's definitely not optimal, and maybe we can find some better lookups later. As a conclusion, promising benchmarks obviously need a lot of cleaning. We need to choose a hash function, but that's not for today, and to double the performance, and we are going to be good. That's it for me. Thanks.
Amazing. Thank you, Emile. Emile has been working extremely hard to de-risk binary fields for us. Yeah, the performance is definitely good enough that we had a lot of conviction in moving in that direction. And there's all sorts of improvements that are going to be incorporated in the weeks and months to come. Any questions for Emile? If not, let's move on because we're very, very tight on time. Thank you so much, Emil, again. Next up, we have Tamir and Eugene, who will talk about a binary version of SP1.
Okay, now I'm not muted. Can everyone see my screen?
Yep.
Nice. Okay. Now it's doing auto slideshow for some reason. Sorry. Okay. Yeah, so one of the main motivations for Flock, other than really originating from this work of proving as fast as computing and others, one of the motivations for me was to really use classical hash functions in a ZKVM. And I will try to phrase this as like what I think ZKVMs in the future should look like, and how we're going to incorporate all this in like the next version of SP1. So a lot of this is work in progress. So I'm going to be a little bit more philosophical in the first half, and then Eugene actually will tell us a bit more concrete results. So, okay. So I informally, I want to kind of divide the progress in ZKVMs in the last few years to like 4 generations, or the 4th generation is not here yet. So the first generation was just being able to like create easy proofs from code. Like at the time, it was revolutionary with risk 0 as the first one, and then SP1, and then others. But in the beginning, it was mostly CPU based, not really cost efficient. And then the first adopters were kind of not latency sensitive customers, but people who had very complicated code bases and wanted to be able to prove something. So this is something like bridges, like Celestia, famously, and unrollups. The third kind of Gen 3, I would say, is like the latency focus, which is the last year's kind of real-time proving effort, really brought new paradigms in how execution and proving are being overlaid. And we kind of see this like convergence of many VMs to like a similar design here. And the question is, what do we require from the VM of the future? And I think a few desiderata that I would like to have is, and some others would like to have too, is formal verification, with AI should be possible. Using traditional hashes only increases our security assumptions. 128 bits of security, some people are already there, others are in progress, and better performance in general. Now, what does that mean? Like, what do I need from the proof system? So hash-based ZKVMs, they all kind of converge to something. They're all very different, actually, when you look under the hood. But when you look from far enough, they're very similar in what they require from a proof system. They require multiple tables because we realize that specializing circuits brings much less overhead on things like zero check. So we need multiple tables with low overhead and the ability to write specific circuits, and maybe also include precompiles. And we need some way to communicate between the circuits. Okay, I think a lot of people here know that. And then another thing we need is recursion. We need an efficient way to enable parallelism and also handle long execution traces. And until now, recursion performance relied on using hash-friendly, ZK-friendly hash functions. And like Justin phrased it, now we will use hash-friendly snarks instead. Namely, I think binary filled snark is a good candidate here. And finally, for a ZKVM where your proving is usually done in server side, you want hardware friendliness. So, originally Plonky 2, or originally the small field quest was kind of motivated by this. And this is to enable real-time proving on modest GPU clusters. And as we heard today, like numbers of GPUs going lower and lower, but GPUs are still the compute throughput machines of today. So then the question is, what does the fourth generation SP1 look like, and what do we adopt? So I think Flock V2 is actually a good candidate. And that's kind of what the message I wanted to give in this first part of the slides. And why? Multiple tables, like I'm kind of repeating something that Ron already said. So multiple tables using the jagged PCS seems to be pretty efficient. The communication, right now we have a grand product argument. I think one very overlooked advantages of binary field arithmetization is that there's no range checks. So that's very nice. So we actually, I think we can do all of SP1 without, we don't need multiplicities. We can just use a grand product argument. And maybe better things like from the likes of the works of Benedict's group in the future. Recursion, as we can see, can verify its own circuit. Like, well, now the key question is like, is it hardware friendly? Notoriously, this is the problem with binary fields. But recently we have been rescued, so I'll pass it on to Eugene to explain more how Flock looks like on GPUs. And Eugene, maybe you can share your screen because it'll be easier.
Or
so pass.
Yeah,
whatever.
can you just do it because it's like yeah. Yeah, so next slide. So yeah, thanks for passing it along, Tamir. Also, sorry for making everyone listen to my coffee grinding at the very beginning. But yeah, so basically, I'll be really quick. So binary fields, the conventional wisdom, or at least that's what we felt internally, was that binary field arithmetic is slow on the GPU. GPU doesn't really have built-in support for binary fields like CPUs do. CPUs, for example, have very fast 8-bit binary field support. However, recently, next slide, as of May, CUDA 13.3 has support for a carryless multiply and add instruction. So basically, it's possible to efficiently implement the G-hash field on GPU. So you can get a 128-bit binary field using this new PTX instruction. So yeah, so basically this, so it's a 64 times 64 to 128-bit carryless multiplication. So you also need caret suba. So between that, so yeah, next slide. Between this instruction and caret suba, we implemented a GPU prover for Flock. We didn't use AG skip yet, but yeah. So roughly early benchmarks is around 7 million Blake 3 compressions per second, including, as far as I can tell, witness generation and proving. This is on a 5090. Yeah. And then the other optimization that I want to mention here is that on GPU, you're sort of more memory limited. So trading compute for doing more compute and doing fewer memory passes, memory traffic helps. So we did this look ahead optimization. So you could do multiple rounds of sum check messages by one pass over the data. And then if you want, you could try it yourself. We merged it into Flock main. You can see that you can get proofs that verify with the Flock verifier. So yeah, so you can just take the main branch of Flock and then run the unit test to do it's a 2 to the 19 hashes here, or 2 to the 20 hashes, the test that I have here, and it'll print you the proving time. Okay, that's all I have.
Amazing, thank you. We got so lucky on so many fronts. All the stars are aligning, and NVIDIA has exposed this new instruction. And this is a great segue to our final talk, which is going to be about GPU acceleration of binary fields as well.
Just wait a second. I need to turn off all the browser. Oh. I think I have a problem with sharing the slide.
If you send them to me, I can use my screen.
Okay, thank you. Okay. Oh, sorry. I sent through the message.
Nice, perfect.
Chat.
Just a second. Share. Boom. Okay. Go ahead.
Okay. Yeah, my presentation is going to be very short. So yeah, we achieved 4.1 million hash per second on single RTS 5090. But unlike the Succinct team does, we did it through the compiler approach. So unlike the existing approaches, we write our protocol in Python, and so there's no CUDA code in the Python code. And then if you look at all these layers, we're starting from the prover layer, which you describe your protocol in Python. And here we have two layers. One is structured, which is a protocol for Frog written in Python based on George. And George stands for Python for GK, which allow you to easy to write your GK scenario by layering. So you can layering IOP and you end up with creating a new scenario basically. And through from the Python, you trace your Python code and you get the IR, which is stable ratio. And then from the stable ratio, we're going to compile it, and we basically modify the something called X-ray, which is X-ray linear algebra. We added some optical on top, and then we make it to aware of the field aware semantics so that it can be lowered to CPU binary, so that from one compiler, if you write one compiler, then it can support basically many arbitrary hardware. So basically this code run on CPU, and because I was so rushed, so I was also trying to support Metal too, but I was so rushed I couldn't make it. But yeah, it basically run the same code, but from Metal 2. Could you go to the next slide? So then the main message about this presentation is going to be, for the 5 weeks, maybe the number is going to be not the latest. So I looked up the entire approaches made by the Snark.fest, and over the entire 2,166 submissions, only the 226 the patches actually moved the performance. And then if you look, if you just pick only the patches that actually move the performance more than 2%, is going to be just 90 patches. And out of entire 90 patches, that if you see categorize all the changes, then only the 15 code changes are actually does nothing for the prover code. And this prover code I mentioned in the earlier page is about fractures and George. So if you write your protocol, the most of optimization is already done by compiler side. Only the 4 out of 19 is really the change you need to make on your prover side. And also, if you look at the frontier code, because maybe this is written by AI, there are a lot of repetition, there are a lot of inefficient code I can find. For example, like if you see this corner for dedicated corner for zero check. If you see some of the cross super multiplication implement in zero check, but not in entity, if I remember correctly. And if you have a hardware you want to support more and more, basically you need to repeat your code. Also, you can find this in the second axis handbit generators. You can also see something like generator that generates the hardware dedicated code, which is not portable. But if you look at all this approach from the perspective of compiler, then most of this code generations can be done by the compiler side, and then so that you can share every technique just by using the compiler side, and then on top you have a George which can be applicable for every scheme, and then on top we have a Flock George, and it's just dedicated to your proven scheme. So basically, with that, we can change our mindset. For example, like the compiler, the one that who implement the compiler owns the how to compute, and the other is going to be in charge of what to compute. And could you go to the next slide? And also, if I see how the throughput is computed, then we can start it from how the time is measured. Time is basically the sum of fixed cost plus the C times H, and the FE stands for fixed computation. You can imagine like this is the time taken for every IOP run, because you need to sample something, which is a sequential. You need to stop your pause your error computation in the middle, or it could be the time for the device and host synchronization or something like that. And H is the number of compression hashes, and C is going to be a marginal cost of each hash. And the throughput is computed like H over F plus C times H. And if you go H to the infinity, the ceiling is going to be N1 over C. And as you can see, the fixed cost is going to be impactful when the batch size is small. But once you have batching your computation, then the fixed cost is going to be amortized. And then if you have over the batch sizes, you get the ceiling of 1 over C, and I think the setting that the Snark.fast is using is almost, we hit most of the ceiling part. So the question is like, so as I mentioned earlier, F is going to be amortized over the batch size. The question is like, how do we increase how do we reduce the cost that takes for, like, if you see like simply thinking that how do you reduce the cost taken for the computation for each element or for given the byte or given the data. Would you go to the next slide? So my belief, there's not much left inside a corner optimization. So if you see the performance in this way, so the y-axis is going to be an attainable performance, and which can be computed using a minimum between compute peak and intensity times bandwidth. And the compute peak is going to be theoretical, the maximum performance you can achieve given your data. And intensity is going to be like the operation per each byte. For example, like if you use Karapsuba, you're going to use a 3 multiplication, and the byte for this operation is going to be 64 bytes times 3, kind of. So, and then if you fix the one device, the bandwidth is going to be fixed. So it's going to be bytes per second. And if you run a profiler using NCU, then you can see where you are, and you typically it sits on the left side of the slope. So if you are in the left side of which means on a slope, then which means the computation is memory bound or bandwidth bound. And if your computation sits on the horizontal line, which means you are computation bound. And because if you analyze, if you profile your computation, is normally in case of a fluctuate, the computation is sitting on the slope of the memory bandwidth, and then the typical way to make your point to the left upper side is basically the technique called fusion or tiling or recomputation. You need to reuse this byte. Fusion allow you to reuse your byte or reduce the bytes you need to transfer from host to device, or tiling also the way to compute the data from the cache or share memory, or recomputation is like basically the recompute from the data already on your memory. And the typical way to achieve so much high performance in AI area is, given bandwidth, you reduce the number of bytes to send, which means you use a smaller sized data, which means like FP4, FP8, like under 1 byte. In that sense, if you look at the way you compute in the GPU side, then I think the research side to pick up the binary field for the next generation proofing scheme is the right choice, I think. Could you go to the next slide? And so as I mentioned earlier, so throughput is going to be sealed by the 1/c, and to reduce the you went too far.
Yeah, sorry, Ryan. We really do need to wrap up very, very soon. Sorry.
I see. Okay, so yeah, all the details are written in the blog, so please scan the QR code and see the detail. And if you have any questions, please DM to me or chat with me. I'm happy to chat.
Awesome. Thank you so much, Ryan, for this completely new direction that doesn't involve writing CUDA, makes use of compilers, super convenient, super portable. We've had a marathon on the Ethproofs call. Thank you so much to the 80 people who've made it 2.25 hours in, and I'll see you at the next call. Thanks, everyone. Bye, guys.
Bye-bye.
Bye.
Bye, thank you.